Linear Programming 7.5 Part 2. In this session, we're only going to do word problems, and I'll show you how to solve them in Desmos. So here are our objectives. You want to write a compact linear programming formulation based on a narrative describing the problem. You want to be able to define the variables, write the objective function and the goal, that is, whether to maximize or to minimize, and write the linear inequality constraints. The second objective is to solve the formulated linear programming model using a graphing tool. In this class, we are using Desmos. So you do that by getting the feasible region of solutions, by solving the system of linear inequalities in the graphing tool. We don't want to do this by hand because the narratives can be quite complicated. And then we evaluate the objective function at the corner points of the feasible region and determine the winner based on the goal. And the last objective is to write a contextualized answer to the original narrative describing the linear programming problem. Recall the Calamity Aid narrative from the virtual class day number 5, 7.5, part 1, where we solved the Calamity Aid problem, but I didn't show you really how to formulate the objective function and the constraints in detail. The point of linear programming 7.5 part 1 was to show you the algorithm given an objective function and the constraints, how to get the solution. For part 2, we are focusing on word problems. So you want to get the practice on how to come up with the objective function and the variables and the constraints. And then everything else will be mechanical because we're using a graphing tool to solve the problem. Let's go back to the Calamity Aid linear programming problem from virtual class day number. I showed you how to solve that problem by giving you the objective function and the linear constraints directly from reading the problem and by showing a little drawing here and there. This time I want to show you how to read a problem and come up with those parts of the linear programming formulation: the objective function, the goal, the variables, and the linear constraints. The rest will be mechanical because you will solve the problem in Desmos. Suppose we haven't read this before. We're reading this for the first time right now. Containers of bottled water and medical kits are to be shipped to victims of an earthquake by plane. So picture it. You're in the middle of the situation. You heard about the victims of the earthquake, and people in your community are going to ship bottled water and medical kits for the people there. Each container of bottled water will serve 10 people, and each medical kit will aid 6 people. Now, I suggest that here you ignore the numbers on first reading. So just remember that there's a container of bottled water, forget about the 10 people. There's a medical kit, forget about the 6 people. So you have containers of bottled water and medical kit. These are the things that you want to maintain in your mind: the earthquake, bottled water, and medical kits. Next, the plane can only carry 6,000 items. Don't think about the 6,000 items. All you will get from this is that the plane has a capacity. Next, the plane can also carry a maximum total weight of 80,000 pounds. Again, ignore the detail. You just know in general terms that it has a maximum weight that it can accommodate. And then more details are given. If a medical kit weighs 10 pounds and a bottled water container weighs 20 pounds, how many containers of water and medical kits can be shipped so as to maximize the number of people who are helped? You will not focus on the numbers, but you will focus on this because it's a question. How many containers of water and medical kits can be shipped so as to maximize the number of people who are helped? Maximize. That's a key word here. So without paying attention to the details of the narrative, what is the goal? You can tell from this one that it is to maximize. Now your next question is, what is to be maximized? And the question helps you find that out. You want to maximize the number of people who are helped. So this is where the objective function will come from, and that is your goal. Knowing what is to be maximized, you can now decide on the variables. So you read the problem again. By the way, don't erase anything. Don't write on the problems the way I'm writing, okay? Because it will be hard to erase. Now you pay attention to the details a little bit. Remember what items are being shipped and how are the people going to be helped. So now you go to the detail. Bottled water will serve 10 people. Medical kit. The plane is going to ship medical kits and containers of bottled water. So these are the items. This gives you the variables then. So you will say that the X is for the bottled water containers and Y is for medical kits. And then you ask yourself, what about the bottled water containers is going to be in the X? Is it the weight? Is it the volume? Or is it just the number of bottled water containers? The question how many containers and how many medical kits tell you what exactly this quantity is. So it's the number of bottled water containers and the number of medical kits. Because now you're going to focus on the first detail, which is here. Each container of bottled water will serve 10 people. And notice that when we are trying to do the objective function, we are actually ignoring this other information, the constraints, and this one too. Okay? So we are looking at this ratio. Every bottled water container helps 6 people. And every medical kit has a cross, will help how many people? Oh, sorry. The bottled water will help 10 people and the medical kit will help 6 people. So you can imagine like associating 10 people with each container and 6 people with each medical kit. So if there are X containers of bottled water, then 10X is going to be the total number of people helped by X water containers. And same thing for medical kits. If every kit will help 6 people, associate those 6 people with every kit. So if there are Y kits, a total of 6 Y people will be helped. So in answering this question, what is to be maximized? It's the number of people who are helped, and that's a total. The total of the number helped by the bottled water containers and the total helped by the number by the Y medical kits. So we have the variables and we now have the objective function. It has to be the total of these two, 10x plus 6y. So this is what we got. Now we look for the constraints. Because we have already done the objective function and the variables and the goal, which is to maximize, we can ignore the sentences that gave us those information. I can ignore this and this because the objective function came from this. 10 people per container of bottled water and 6 people per medical kit. I also don't need the question anymore because That gave me the goal and what I need to maximize based on the narrative. So I only focus on what remains. So let's read the first one. The plane can only carry 6,000 items. So that's a cap. So the total it can carry is less than or equal to 6,000. If we make it 6,001, that extra item cannot make it inside the plane. It will be rejected. So this is counting medical kits and containers of bottled water. That part gave us a constraint. So knowing that X was our variable for bottled water and Y for medical kits, the total number of items would definitely be X plus Y, and it cannot exceed 6,000. So that's our first constraint. Notice we ignored the other sentence because we were able to capture a constraint on this single sentence. Again, we read the problem, ignoring the sentences that gave us information that we have already used. And that would be this. We don't need that. Don't need the question. So we're left with two sentences. Plane can also carry a maximum total weight of 80,000 pounds. Again, this gives us the total weight is less than or equal to 80,000 pounds. Now the weight will come from the weight of the medical kits and the weight of the bottled water containers. But there are Y medical kits 10 pounds each, so the total weight would be 10Y. And there are X containers of bottled water, each one weighing 20 pounds. So that's 20 pounds times X. So this would be the total weight. And this cannot exceed 80,000. Another way to see this is to use dimensional analysis. 20 pounds per water container times X water will give us, cancel, it will give us 20 pounds times X, which is 20X. Okay, there. And similarly for Y. So we have this constraint. So this gives us our complete linear programming formulation for the original narrative for the Calamity Aid problem. This is the LP formulation. It's very compact. We will now use Desmos to solve this problem by just entering these constraints, and then later on, after getting the feasible region, by entering the objective function and calculating its values at the corner point.